So.
I don't. I'm lost.
Okay, that's all right. Anyway, I don't remember exactly where to go from there. I knew once, but I don't know. But that's Pascal's triangle. And it's a mathematical relationship that applies to this because of the way that these lines overlap when your j's are all the same, have the same size.
Okay.
Right. So that's a quartet. What it is really is it's three separate doublets, but the doublets start to overlap because all of the j's are the same. So here's a doublet, here's a doublet, here's a doublet, but in the end, you don't see three separate doublets, right? So you don't see, what is that, 2 lines times, you don't see 8 lines or whatever. 2 to the third, you see 4 lines because you get this redundancy or this overlap.
Oh, okay.
So quartet is kind of like 3 doublets with the same J. A triplet is 2 doublets, but they have the same J. A doublet of doublets is 2 separate doublets that do not have the same J. And that's what we mean specifically when we say doublet of doublets. So 2 and 10, 4 and 12, whatever, but the J values aren't the same.
So they all come from a doublet, right? It's pretty much just drawing.
That's right.
Doublets.
Every coupling, every individual relationship between 2 hydrogens is just a doublet. And so every single one of these, no matter how complicated it gets, in principle, you can figure it out by just treating each single one of these as a doublet and then just working your way through your tree from the top to the bottom and just spreading it out. And it gets a little more complicated when your J values are different because you don't get that overlap. That's why the n+1 rule doesn't apply for doublet of doublets. It only works when all the J values from all the talk here match and they're all the same.
So when you do these trees, you're only looking at 2 sets of non-equivalent hydrogens at a time when you're...
Well, yeah, that's how you get the doublet of doublets. But remember here that these 2 are probably equivalent. In other words, if this is swiveling around and this hydrogen sees these 2 as being essentially the same and it has the same coupling constant, that's probably because HA and HB are really just part of an equivalent set. It's just a CH2 group, and there's no difference really between A and B. So it's almost like in this case here, the triplet or the quartet, A and B are equal. Okay, they're equivalent. And therefore, the coupling constants between the star and the A and B are also the same. Right, so the star to A coupling constant and the star to B coupling constant have the same value because proton star can't really tell the difference between A and B. In this situation, right, where we talked about if it's locked down so that A and B are either perpendicular, let's say one's perpendicular, one's anti-paraplanar like this, the star proton senses a difference between A and B. And in a situation like that, more often than not, the reason for that is that they're occupying different environments in the molecule, and they're kind of locked down to some extent in those environments. And usually what that's going to tell you is that A and B are also going to be non-equivalent. Because when they look around, A and B have different environments. They're close to different things. They see different things in the rest of the molecule. So this type of situation happens most often. In other words, where these 2 coupling constants are not the same. Usually that's because these 2 protons are not the same. In other words, they don't absorb at the same frequency.
So you can only know that if you have the J's first, but if you just had a picture, you couldn't go back.
To really confirm that it's true, usually the J values helps. But you can look at a picture and usually make predictions about whether or not the protons are going to be equivalent or non-equivalent. Right? I think there was a quiz or a test question earlier in the semester that was kind of related to that. Where you've got a molecule and you have a few different hydrogens in the molecule, and you have to try and figure out which one of these couplings is going to give you a doublet of doublets.
No, I remember that. That's when I skipped.
It's like, nah, forget about it. Well, anyway, I mean, the basic idea, I don't remember for sure what the molecule was. I think it was something kind of like this. There's like I was talking to someone about this in the last week or so. I think it was something like this. There was an ester or a ketone or something over here. There was, I think, an ether over here, so like an OCH3. So you had these 2 hydrogens.
And you circle both hydrogens.
Yeah, and then you had this one, and then I think there was a methyl here. Right, so the question, one of these is going to be a wedge and one's going to be a dash. The question here had something to do with, you had a spectrum for this molecule, and it showed a couple of doublets, DD patterns like this. There were 2 of them in the spectrum, and the problem was asking, okay, can you identify which hydrogens in the molecule are likely to have a DD pattern as opposed to a triplet or a pentet or the quintet, I guess, or whatever. Okay, so for example, when you look at that hydrogen, how many neighbors does it have?
2.
It has 2 over here, but look down in this
Oh.
direction. Right?
5.
So yeah, it's the sum total of all its neighbors, right? So it's actually going to be at a minimum a quintet, but it might even be more complicated than that if it has a relationship to some of these protons that are non-equal. In other words, if the J values aren't the same for this, and this, and this. But at a minimum, it's going to be a quintet, right? So that's not likely to give you a doublet of doublets, right? So now when we look at the methyl group over here, how many neighbors does it have?
2, huh?
Well, it has 2, but remember, this drawing is kind of terrible because I ran out of room, but this methyl group's attached to that oxygen's attached to that carbon.
So you can still count that?
Yeah, so we wouldn't count it in that case because it's insulated from those hydrogens. It's too far away.
So just
So it's
1.
It's 0 actually. Okay, here, let me draw it again.
Well, there's 3 H's. Are you counting from
The 3
H?
H's, all right, but if we consider this to be a group, right?
No.
All right, so you're right. I mean, within that methyl group, if it turns out that those 3 hydrogens are not equivalent, in other words, if they have different environments and they absorb at different frequencies, then you've got to sort all that out. But usually, a group like that, these 3 are going to be equivalent. In other words, that group.
Why are you counting those as individual ones? The ones
These
divided, yeah.
down here? Well, I'm looking at this one, and I was asking, okay, how many neighbors does it have?
So what were you looking at just now? As the H by itself?
Yeah, this H right here.
No, just now.
Over here?
Yeah, you was looking at one of those H's?
Yeah, one of those H's. Now, the question is how many neighbors does it have? And before you answer that, you've got to figure out first, are all 3 of these equivalent or are they non-equivalent?
It probably would be equivalent.
They're equivalent, right? Because this group's kind of like its own little unit. It's swiveling around. And so these 3 in this methyl group are equivalent. Right? What that tells you, if they're equivalent, they absorb at exactly the same frequency and they don't couple
Oh,
to each
so
other.
they're a singlet.
That's right. That one's just a
Oh,
singlet.
okay,
So
never
you don't have to. There's nothing to worry about with that one. Okay. And moreover, since it's insulated, not only do these not couple to each other because they're equivalent, but they can't really talk to this one because there's an oxygen in the way. There's too far away. Right. The only kind of 4-bond coupling you ever really see is when there's some sort of an alkene or a benzene ring in the way here. So, for example, every once in a while you'll see a very small coupling like this. There are 4 bonds separating these, but that's unusual, right? In this case, you have 1, 2, 3, 4 bonds separating these, and that's too far. So they don't talk to each other, right? However, let's go back to these other hydrogens over here. Okay? So this has 5 neighbors, right? Let's assume that these are all equivalent on this methyl, and it's a pretty safe assumption that they are, right? How many neighbors does this guy have?
3?
Okay, well, it is 3, right? The group of equivalent hydrogens is 3, but when you look next door, how many neighbors does it have?
1.
Just 1, right? 1 neighbor next door. So again, let's say that if there were no hydrogen there, what would this look like? What kind of pattern would it be?
A singlet.
It would be a singlet. Okay, now when we introduce 1 neighbor, what does it become?
Doublet?
It's a doublet, right? So this group is split by this one. So we have 1 coupling, but these 3 are all, this is sort of like our star now. This whole group is an equivalent set. So we basically treat this equivalent set the same way we would treat this 1 equivalent proton, one individual proton. Because these all come together as a unit. They all absorb at the same frequency. And they can't couple to each other because they're already at the same frequency. All right, so this will be a doublet. It has 1 neighbor. All right, we figured out this one's got 5 neighbors. It's probably going to be pretty complex. All right, so the only ones we haven't talked about yet are these 2 hydrogens. As it turns out, these 2 are going to be the ones that are represented as DDs. They're doublet. Each one is a doublet of doublets. All right, so we got to try and figure out why that's true.